Okay. It says the function f has a Taylor series about x equals 1, and it converges to f of x and for all x in that interval of convergence, whatever that may be. It is known that f of 1 is 1. It also gives me first derivative, and it gives me a way to calculate any other derivative using the formula for the second derivative and beyond. So we want the first four non-zero terms and the general term for the Taylor series. Okay, first term is f of 1, which is 1. Second term is going to be the first derivative, which is 1/2, times x minus 1 to the first over 1 factorial. To get to the second derivative, we need to use this formula, and we're just going to plug in 2 in for n. And if I do that, notice here, I'll go ahead and get -1 squared. It'll be 1 factorial on the top, which is really 1, and then 2 squared on the bottom, which is 4. So I'm going to write it as 1/4, and then I have x minus 1 squared over 2 factorial. And then I need the third derivative, so I'm going to do the same thing. I'm going to plug in 3 in for n, and if you do that, you should get -2 over 2 cubed, and then I'm going to have x minus 1 cubed over 3 factorial. So there's my first four non-zero terms, and then I want the general term. So I have a formula for the general derivative, so it's going to be -1 to the n minus 1 factorial over 2 to the n. But then notice that only gives me this number in front. I need to use this also. So I also need to include x minus 1 to the n over n factorial, and then this is a series, so we want to make sure we put that plus ... So there's part A. Okay, for part B, it wants me to find the interval of convergence. Remember, for interval of convergence, you only have two options. Either you're going to use the ratio test or use the geometric. This is my general term that I came up with here. It's not a geometric, so I'm going to use the ratio test. Now, before I use this, I'm going to go ahead and clean this up. So this is what I have. And one thing I'll notice is I can go ahead and clean this and this up. Because really this is n minus 1, n minus 2, ... This piece down here is n minus 1, n minus 2, ... So this and this will drop out. So really you'll just have the n left on the bottom. So my general term looks like this. So remember, the idea is you don't need to simplify it in your answer above, but if you're going to be using it for the next step, I typically like to clean things up. So now I'm going to go ahead and do the ratio test. So the limit as n goes to infinity, absolute value, we take the n plus first term, all divided by the nth term, so flip it. So this is my setup. And you will notice lots of things will drop out. The negative ones become unimportant. You'll have the 2 to the n. So if you want to do an extra step in here where you clean things up, really you just have an x minus 1 to the first, a 2, and this. And then now when you take the limit as n goes to infinity, the limit is just x minus 1 over 2. Ratio tested, it only converges if it's less than 1. I'm going to solve this, so really move that 2 over, rewrite it without the absolute value, and this is what I get to. Now, it's asking for intervals, so I do need to check the endpoints. So I'm going to check x equals 3 first, and we're going to take that and we're going to plug it back into the original general term for x. So if I do that, this is what I end up for. Oops. So I'm plugging it in here. So I still have the -1 to the n. I end up with 2 to the n, 2 to the n, and these drop out. So really, this is what I end up with. And I know this is going to be converges because it's an alternating series whose absolute value of the terms decrease to 0. Oops. Okay, and that's my reason for that. Now let's do the same thing with x equals -1. So again, I'm going to go back up here and plug in -1 for x. So if I do that, I end up with this. notice what happens is the 2 to the n's will still drop out, but I'll be left with the negative 1 to the n here. But then a negative 1 to the n times another negative 1 to the n is negative 1 to the 2n, which is always positive. So this really simplifies to this, which is a p-series that diverges. So my final interval is going to look like this. It's going to converge at 3, but diverge at negative 1. So my answer, or my interval, should look like this. Okay. Part C, I'm going to go ahead and erase some of this, is asking us to approximate f of 1.2 using the first 3 non-zero terms. So all I'm going to do is go ahead and go back to my series that I created in part A and just use the first 3 non-zero terms. So, and I'm going to go ahead and plug in, so this is part C, 1.2 for x. You can leave your answer like this. If you had a calculator, you can punch it out. It ends up being 0.905. The last part says, show that your approximation in part C is within 0.001 of the exact value. So it wants you to show them that the error is less than or equal to 0.001. So 2 errors, either alternating series or Lagrange error bound. If I look back at the original function, I do notice it is an alternating series. So we are going to say, it actually did say in part C it was an alternating series. So we are going to use, we know that it is an alternating series because the absolute value of the terms decrease to 0. So because this is true, we can use the alternating series error. So in part C, we just went to the 3rd term. So your error just comes from the next term over, which is this. So this is my error. And for error, we want absolute value. And we are plugging in 1.2. So this is my error. And you can go ahead and clean things up and use your calculator to double check, but it is less than or equal to 0.001, which is just your check.